Hey everyone, welcome back to Calculus 2. This is going to be lecture 20 of the course. And in this lecture, this will be a shorter one, lecture on the shorter side. We're going to discuss integration by tables, like tables of integrals. So, so far, we've learned a lot of integration rules and they've all kind of relied heavily on our ability to recognize patterns in how the integrand is structured. Integration by tables really kind of takes this to its logical extreme by basically making integration pretty much 100% about finding the correct pattern. Okay, so let's go ahead and jump into this. As I said, I think this will be a shorter. We'll do a couple examples, talk a little bit about some of these integration formulas, and probably be done a little early. So we're going to go ahead and call this section, let's see here, we'll call this section 3.6, integration by tables. Okay. So, as I said, we'll make this a little bit on the briefer side as far as lectures go. But, if you're in the sciences, like maybe if you're studying physics and you go to graduate school for physics or even an undergraduate, you're going to run into this integration by tables. And I suppose the engineering disciplines as well. Mathematicians, we're interested in this, but this is going to be basically like, how can I calculate integrals that are really complicated that there aren't any basic simple rules for. Well, in a lot of cases, you can fall back on work that other mathematicians have done to identify integration formulas that match certain patterns. Okay, and so integrating by tables is all about pattern matching. Okay. There are many resources that'll have different integration tables. Like any textbook will have a whole section dedicated to integration tables. Let's take a look at a resource online. And so this is openstacks.org, and they have a collection of integration tables that we can look at here. And so just kind of glancing through here, you can see some of these are basic integrals that we've learned, right? This upper section in particular. Here's some trigonometric integrals, right? Things that we've seen. Some of this we've seen with our trigonometric integration section a couple sections back. We've seen some of these. But as you can see, this is a much more comprehensive list of integrals that can be identified using these tables. So here's some additional ones, things that we haven't necessarily come across, some exponential and logarithmic integrals, right? You can notice everything's everything's A's and U's, right? So hopefully this will coalesce well with like the integration techniques we've used thus far. Just kind of scanning through here, you can see, they're more or less complex, some of these integrals involving a squared plus u squared. So we've seen some of these obviously, but many more here, right? So, and this is actually what I would tend to think of as kind of a limited list of integrals. I've seen some that are hundreds and hundreds, not just 100. But basically, all of these formulas in here, can be verified, right? You could spend the time working on any one of these to verify that these formulas are true. Let's take a look at an example, one that I've spent a little bit of time ahead of time verifying, this 84 part B. Okay, so let's take a look at this 84 B and just verify this, and so we can see kind of a little bit of what's at work when we're working on this. So let's verify the following. Okay, so we've got the integral of du over u squared minus a squared. Okay, so when you have an integral of that form, then it's equal to 1 over 2a times the natural log of u minus a over u plus a. Right. Okay, so that's the form. So let's take a look at this. So again, the point of integration tables is so that you don't have to figure out every integral from scratch. You can, kind of build on the work that others have done previously. But let's take a look at sort of what's behind some, an example of what's behind an integration formula. All right, so one thing we'll start with this integrand, and we'll do a little algebra to it. So 1 over u squared minus a squared. All right, we'll start with that. Now, that can be factored into 1 over u plus a times u minus a, right? And that's relatively straightforward. Okay, and further, this can be written as 1 over 2a. Now this is, a little bit of a tricky maneuver here, but you've got the u plus a on the bottom, the u minus a on the bottom, right? Now up top I'm going to write u plus a, right, that in parentheses, minus u minus a. Okay, now notice here you get a u minus u, right? So u minus u is 0, and then you get an a minus negative a, so a 2a on top. So the 1 over 2a is the same as the 2a on top here. Okay, right, and then we can take this thing and we can break it up, right? So in particular, we can see that this is equal to 1 over 2a times 1 over u minus a minus 1 over u plus a. Okay, and so basically what we've done is we've rewritten this expression here into something that we can kind of easily integrate. Okay, and so what that means then is that the integral of du over u squared minus a squared is equal to the integral of 1 over 2a times 1 over u minus a minus 1 over u plus a. Right, like so. Right, and then so of course this looks more reasonable because this is just 1 over u minus a. Basically, we can integrate that to natural log, right? So let's go ahead and break this apart. This would be written as 1 over 2a times the integral of 1 over u minus a, and I guess technically minus the integral of 1 over u plus a, and I'm going to put the du on top here. Right, like so. Yeah, and so then this one is really easy to integrate. We've got 1 over 2a, and then this is just the natural log of u minus a minus the natural log of u plus a. Okay, and then plus c, of course, on the end. Right, and then we can do some work here to clean this up. So when you subtract logarithms, you can rewrite that as division. So this would be 1 over 2a times the natural log of u minus a over u plus a plus c. And so then, of course, that is what we're aiming for, right? So we can ditch the parentheses, I guess. U minus a over u plus a plus c. Okay, so that is what we're headed towards, right? And so you can see that this integral isn't like super crazy. There's some tricky algebra, right? Some kind of tricky algebra here, but then it's pretty straightforward, relatively speaking, right? Some of them are like this. Some of them are far, far more complicated, right? So this is just an example of how you can verify any of the integration formulas that you will encounter over here. Okay. Okay, very good. All right, let's do an example here of actually using these formulas to calculate an integral. Okay, so the question here would be, how do we fit, our integrals, to the forms given by the tables? And so let's do a few examples. Okay, let's start with this guy. Let's evaluate the integral of dx over x times the square root of x minus 1. Okay. Now, there's a subtle art form to this, clearly. You know, one of the things that you can see here is that, you know, this integral involves the form a plus bu. Right? Really, it's, in our case, it's bu being the x and then minus 1 being the plus negative 1 being the a. Right? So let's look at the section that, you know, has forms involving this this a plus bu square root. So let's look at the section of the tables that deals with a plus bu form, right? Okay, and so we can just jump out there and start looking around. And so, you know, kind of jumping down here a ways. Let's see, I went too far here. Let's see. Here's a plus bu, right? So some of these are square roots, some are not. Let's see here. So here's one. This would be kind of what we're targeting, right? So our integral is x times the square root of x minus 1. And we can see that number 108 here is u times the square root of bu plus a, right? So this is what we should probably start with, right? Now, I've done the work ahead of time, so I know that this is the one we should start with. But in reality, it's maybe not as easy as this, right? So, you know, you may have to pick and choose a little bit. Maybe you think 107 will work, you try, it doesn't work out. Maybe 108, and then you know, maybe you skip around before you land there. But let's try this number 108. All right, so the form looks like this. The integral of du divided by u times the square root of a plus bu. Okay, and then supposedly that's equal to 2 over the square root of negative a times the inverse tangent of a plus bu over negative a, and this is all square root plus c, right? Now, notice we've got the square root of negative a, and so if we look closely at 108, it says, you know, you've got two options here, right? You've got for a less than 0 and for a greater than 0. Now, in our case, the a in our expression is negative 1, right? So we're clearly looking at the a less than 0 case, right? Which is this one right here. So that's the one that I've grabbed, and that's the one we're going to try to work with. Okay. Now, obviously, if a is greater than 0, then you're taking the square root of negative 1 or negative a. You're taking the square root of a negative number, and that is probably not a good sign. It's probably a sign that you're on the wrong track in Calculus 1 if you've got imaginary numbers. So for this one, you know, kind of looking up here at our expression, let's let a equal negative 1, right? That's the negative 1. And then b will be equal to 1. And of course, u in this instance is just x, right? So if u is x, then du is equal to dx, okay? Okay, and then let's just plug everything in here, right? And so you can see, well, let's take the integral itself, dx over x times the square root of x minus 1. Well, and let's just rewrite this a little bit. All right, let's write it like this, square root of negative 1 plus x. Right, and so we can see that this is definitely going to match this form. This is the integral of du, because du is equal to dx. And u is equal to x, so that's a u. A is equal to negative 1. And b is equal to 1. So the b times u is just plus x, right? Okay. And so we know that that is going to be equal to 2 over the square root of negative a times the inverse tangent of a plus bu over, sorry, that should come all the way down, negative a plus c. And so we can quickly just plug those values in once we have confirmed that the form is good. Right, so we get 2 divided by the square root of 1 in this case, so, and then inverse tangent. And this will be -1 plus x on the top divided by just 1. Okay, perfect, right? And so then that means we have, as an answer, we would have 2 times the inverse tangent of square root of x minus 1 plus c. Right? So as you can see, the whole method here is literally concerned with basically taking the given integral and mapping it onto a form that's been identified in the integration tables. Okay. Excellent. Let's try another one. Let's try this one. Let's evaluate the square root of x times x times the square root of x to the 4th minus 9 dx. Okay. Now notice here that, you know, the radical here obviously has the form of u squared minus a squared. So note the radical has the form you know, u squared minus a squared. So basically x squared squared minus 3 squared. Okay, so let's consider, so let's look for this in the tables. Okay, so just jumping over here, let's look for anything that involves u squared minus a squared. So here's a whole section, u squared minus a squared with a greater than 0. So in our case, a is 3. Right, so just kind of glancing through here, we see, you know, number 77 here has a u squared minus a squared. So let's mess with that one. Okay, let's play with that one. Okay, so let's write this out here. So in this case, the integral we're looking at is u squared minus a squared square root times du. Right, so just kind of looking at what we have. So let's if we let u equal x squared, right, then du is equal to 2x dx. Okay, and obviously we'll say a is equal to 3. Okay, right, and so then kind of starting with that, can we rewrite this in this form? Right, so the integral of x times the square root of x to the 4th minus 9 dx. Well, this calls for a 2x dx, doesn't it? So let's do the old 1/2 times the integral of 2x trick. Okay, now do we get the substitution? You bet, right? So look here, here's our u squared minus a squared piece, and the 2x dx is our du. Okay, so we can plug everything in here. So this would be 1/2 times the integral of u squared minus a squared du. Right, and so we can basically use the form for this, or sorry, for this one up here, but just with a 1/2 in front. Okay, so I'm going to write that all out real quick, just because I don't want to have to switch back and forth. Let's go ahead and write out what this integral should say. It should be u over 2 times u squared minus a squared, square root of that, minus a squared over 2 times the natural log of the absolute value of u plus, and then it's the square root of u squared minus a squared. Okay, that whole thing plus c. Okay, so kind of a beast, right? So this right here evaluates to this, right? Of course, the 1/2 is out front because, you know, we had to use that in order to get the du substitution, right? So now we can just plug in our values, and away we go. So u is x squared, right? So this would be x squared over 2 times the square root of x squared squared. So I'm going to write it all in here just to be really thorough so people can follow the substitution. And then it's minus 3 squared over 2 times the natural log of, remember u is x squared, so that would be x squared plus the square root of x squared squared minus 3 squared plus c. Okay, and so that's basically it. And of course you could do a lot of cleanup here. We'll go x squared to the 4th, or x squared over 4, and then it'll be x to the 4th minus 9 minus 9/4 times the natural log of absolute value of x squared plus the square root of x to the 4th minus 9. Okay, so that would be like sort of the more cleaned up version. Okay, all right, and so you can see you just kind of, it's a lot of like go find the appropriate form and then plug it all in. Let's do one more example. So this last example, let's evaluate a trig function here. So this will be sine of 2x over 2 plus cos x. Okay. Now you can look through the tables and you'll find that, oh, you're going to run into a problem looking, finding a sine of something to match that sine of 2x. And so we can change this out right off the bat. So just recall your double angle formula, and that is that sine of 2x is equal to 2 sine x cos x. Right? So just kind of recall that. And so changing the integral right off the bat produces, 2 times the integral of sine x cos x over 2 plus cos x dx. Okay. Now notice that really none of the sine cos forms will fit this integral. If we go out and we look, we can kind of look through some of these trig integrals, and we don't really, we're not in this table anyways. There's no direct sine cos example. But, if we scroll down a little bit, we do see something here at number 98 that maybe wouldn't be obvious right away. But here you've got a u over a plus bu. Right? And so this one actually might fit this just because we have that 2 plus cos in the bottom. Right? So let's consider this one as an option. Right? Let's see what happens. Right? Consider this guy here, the integral of u over a plus bu du. Okay. So what happens if we do this? Let's let a equal 2. Okay, kind of looking back up at this. So we'll let a equal 2, b equal 1. Okay, so the bu, and then of course cosine then will be the u. Right, and then that means that du is equal to negative sine x dx. Okay, so let's take a look at this. So if we have 2 times the integral of sine x cos x over 2 plus cos x dx, right, we can multiply through by a negative here. Right, and we get negative 2 times the integral of, let's see, cos x times negative sine x over 2 plus cos x dx. Right, and so now what do we have? We have, remember, u is cosine, so at the bottom we have the a plus bu. A is 2, b is 1, and u is cos. So a plus bu is satisfied. Now if we're letting u be cosine, then we've got the u up top, right, to match that. And then du we found is negative sine x dx, right? And so this one perfectly matches. It's a little bit unintuitive because you may be scanning around looking specifically for cosine and sine, but this one does work. So this will give you, let's see, negative 2 times the integral of u du over a plus bu. Okay, and then we can just look at the tables and we can see that this whole thing should be equal to 1 over, again, I'm just reading this off the table, 1 over b squared times bu minus a times the natural log of a plus bu. Right, like so. Right, and so we can just plug everything in here. So our b is 1, so this would be 1 over 1 squared times 1 b times u, and then u is cosine, minus a, which is 2 times the natural log of, and then this would be 2 plus cos x inside here, wouldn't it? Right, and so of course this is, oh, and then I'm sorry, you're going to need the negative 2 out front. Let's not forget that. It's important. Right, because the negative 2 here needs to be brought along. So then you're going to end up ultimately with 2 cos x minus 4 natural log of 2 plus cos x plus c. Okay, perfect. Actually, I think this should all be negative, and that should be a positive probably. Yeah. Okay, there you go. So that's another example of integration with tables. Right, and so obviously this greatly expands, the kind of integrals that we can deal with, things that involve like a lot of complicated tricks, like a lot of algebra tricks or even calculus tricks. Can be sort of, you can take advantage of somebody else having done that work already by just sort of plugging into these tables. Okay. All right, so that'll do it for this section. Next time when we get together, we'll talk about indefinite forms and L'Hopital's rule and set up for our last big integration section, which is improper integrals. So dealing with improper integrals, which is actually a very, very interesting section. So we'll see you all then.